Question for you. So certain reasons there's a super likelihood
Dark matter, dark matter. Dark matter.
Dark matter.
Dark matter. Dark matter. Dark matter.
There is a not so bad reason why we are looking for it and why we all think it exists, why something exists that is dark in at least one way, that we can't really detect it. We more detect its effects. Basically, from the smallest scales here in our neighborhood out to the cosmos, we see evidence of something without a guilty party, so to speak, without an actor doing it. And so this is our dark matter in terms of the gravitational effects. And then there is the dark energy, which seems to be expanding the universe, at least from our scientific perspective.
How'd you make a galaxy? The ingredients are dark matter, and then stars, and then gas.
Dark matter makes up about 85% of the mass in the universe. So our best idea for what dark matter might be is that it's some kind of subatomic particle. We don't know what kind, but there are several good ideas which come out of particle physics that provide good candidates for dark matter. And we're looking to see if we can actually detect one of those in the lab.
The leading detectors for trying to find this, the most sensitive, are liquid noble gas, like xenon or argon in liquid form.
We have our milk carton here.
It's not there. It's just not. This dark matter model is probably not completely correct. Taking all these together, it poses a real problem for our understanding of cosmology.
The direct searches are pushing to masses higher than the LHC can reach, and also to cross-sections, interaction strengths that are very weak, much weaker than the standard weak interactions. And that's the direction we push, down in interaction strength and either up or more recently also down in mass. So down to below the mass of a proton or up to the mass of 1,000 protons.
We have had to sort of invoke some tooth fairies to keep things sensible. One of those is dark matter. Supersymmetry is my favorite example. It was a beautiful idea, very compelling, was basically accepted widely in the 80s. All the predictions that supersymmetry made have failed badly. And the most popular form of dark matter, the WIMP, is a supersymmetric particle. So you only have WIMPs if you have supersymmetry. And so now we've gotten to this weird point where most people seem to have forgotten that you need supersymmetry to even have WIMPs. Now we have WIMPs because we know we need to have this dark matter, but the supersymmetry that is required to make those things exist doesn't work. And it's failed in lots of ways.
everything goes back to Newton. Newton didn't just discover the inverse square law. He discovered two more things. One was that knowing the luminous distribution, namely knowing the sun, you could predict the velocities of all the planets. No dark matter. It's absolutely clean and straightforward. That, in my opinion, is the gold standard for what you need to do in any theory of gravity. You have a law of force, you know the visible material that you can see, and then you have to predict the velocities, predict exactly what's going on. That's step A. Step B, he proves a theorem. It's a very interesting theorem. And it says this: if you have a spherical distribution of matter, and you want to know the force at any point, then the only contributions are coming from material within the region where the object is located. Nothing is coming from the outside. The outside absolutely decouples, and therefore, if you wanted to solve for the solar system the way he did, you didn't need to consider any other sources. Okay? Now, the mathematical reason why this happens, the inverse square law force falls like 1 over the square of the distance. But the solid angle grows like the square of the distance, and therefore they cancel. Exactly the same thing happens for Coulomb's law in electromagnetism. So with Newton's law, we have two remarkable things. One is knowing the luminous distribution, you get the velocities, and two, you don't need to include anything outside the system of interest. Now, dark matter keeps the second rule, but not the first. In other words, dark matter says we only need to know what's going on within the system itself, but we don't have to restrict to luminous matter alone. In other words, you give up the Newtonian gold standard right away. And that, to me, is not good physics. Just simply point blank, that is not the right way to approach the problem. Now, a way to think about this, which is very simple, but of course not the complete story, is if you have the inverse square law, then it's true on all distances, including r equals 0, namely at the origin, which means that a particle acts back on itself. We worked for 6 months. The equations are quite complicated, and we managed to solve them, and we found the exact solution. Yes, we got the inverse square law. But we then got something that we absolutely hadn't anticipated, namely we got a second force, and that second force was not vanishing at large distances. The inverse square law gets smaller and smaller. It goes like 1 over the square of the distance. This second force was constant. It did not fall off at large distances. We looked at that. It took us 6 months to find the equations. It took us an afternoon to solve them. And when we got the solution and we saw this extra term, we realized immediately that we could replace dark matter. And that wasn't what we were looking for. And it took me many years to understand this. It took me a lot further steps. I gradually realized that because I had this force which did not vanish at large distances, Newton's theorem that I can ignore the outside no longer holds. And therefore, the outside must be playing a role. That the notion that we can neglect the outside only comes because of a very specific law of force, namely Newton's inverse square law. Any other law of force, you can't neglect the outside. So, if you now go back to the early studies of galaxies, where people measured velocities and found that the velocities were more than they could manage, and so they went on to say, okay, there must be some missing mass. What I say is, it's not missing. It's the rest of the universe. It's been there all along, and it's hiding in plain sight. And you just didn't recognize it as such. And therefore, you should not conclude that dark matter is doing the job.
But this problem with the
too early appearance of galaxies actually goes back a couple of years, and there were already hints that there were major issues with the standard model. And basically, to put it in a nutshell, what it is that in the standard model of cosmology, there's a very firm prediction of what the timeline has been since the Big Bang. And the problem here is that these massive galaxies and the massive dark matter halos from which they formed appeared way too early for standard astrophysics to be able to explain how they came to be. So just to put a number on this, because it's a lot easier, I think, to understand in terms of actual numbers, the redshift at which they see these massive galaxies and halos, which is around 10 in the case of Charles Steinhardt's work, that corresponds to an age of the universe of around, let's say, 600 million years after the Big Bang. And remember that the age today is about 13.7 billion years. So we're talking about something very, very early in the history of the universe, 600 million years or so. The reason that's a major problem is because, as we understand it today, stars could not have started to form until about 3, maybe 400 million years after the Big Bang, because it would have taken that much time for the gas to cool and condense and clump up and form stars. So basically what the data are telling us is that if the standard model of cosmology is correct with its timeline, then these 10 to the 10 solar mass galaxies, billions of solar masses within each galaxy, formed in only 150 to 200 million years, which is absolutely physically impossible as far as we know today, based on the astrophysics of star formation and aggregation and the formation of galaxies and so forth. But to be fair, there were other indicators even before Steinhardt's work that showed that there was a problem with the timeline. Perhaps most famously with the appearance of these supermassive quasars, these supermassive black holes, which started appearing at a redshift of 6, and then today the record is about 7.4. That redshift corresponds to about 800 million years. And so the indication from the appearance of these supermassive black holes so early in the history of the universe is that these billion solar mass objects formed in only 500 million years, which again is not easy to understand in terms of the astrophysics that we know today. The conundrum is that we see these objects, either black holes or these massive galaxies, way too early, and in order for us to be able to explain how they formed in such a short time, we have to exceed what we think can actually happen in terms of the astrophysics of accretion and growth and so forth. So the conclusion from this is either that the astrophysics we have today is wrong, or what we're suggesting is that perhaps the cosmology is not completely right. Ironically, Charles Steinhardt's father, Paul Steinhardt, was one of the inventors of inflation, and Paul Steinhardt is now a total convert the other way. He thinks that inflation is wrong. Even though he was one of the inventors of that, he's actually an inflationary apostate, if I could put it that way. He argues against it.
When things go wrong, you have to bear in mind that maybe we got something wrong along the way, or missed something that is important.
Kirchhoffs claim if you have a cavity and you're in thermal equilibrium with that cavity and the cavity is opaque, the radiation will always be the same inside that cavity, depending only on the temperature and the frequency and independent of the nature of the walls. The ratio between emissive power and absorption power is the same for all bodies at the same frequency, at the same temperature. And then Kirchhoff immediately sets the absorption to 1. So this is an idealized state. And I understand, as anybody who's taken a modern physics course, that this is, Kirchhoff imagines something that's a perfect emitter and he sets absorption to 1. But if I set it to 0 in the perfect reflector, as we hope to have when we do MRI, then that function blows up. So perfect reflectors definitely cannot support Kirchhoffs' claim. And remember, he said it was independent of the nature of the walls. But this is the key thing, and this is what has been missed by physics, is that real black bodies can do work, and perfect reflectors cannot. So we depend in MRI on having a perfect reflector. We don't want it to do work. We don't want our coil to do work on our radiation. We just want it to transmit it, right? And that's the same thing for lasers. In lasers, you have mirrors, and these mirrors are building up waves between the mirrors, and they have quality factors of 10 to the 11th. Now, to tell you what that is, a quality factor of 10 to the 11th, that means it'll hold for every 10 to the 11th wave it's standing, it'll lose one. Well, that's perfectly reflecting, right? 10 to the 11th, no black body has ever approached these kinds of numbers. So perfect reflectors exist, and they're telling us that Kirchhoff cannot be right. So real black bodies can do work, perfect reflectors cannot. And here's an example where I take this block and I put it on a hot plate. The bottom 4 are copper, then graphite. I think the next one is aluminum and then brass. And you can look in the paper for the assignments. But look at the graphite holes. They're all white. Now, they have different depth. The holes on the right, the 4 holes on the right, 3 are black and 1 is white. The one in graphite is white. Those holes are just the tip of the drill bit into the block. That's all that there is there. Okay? And then as you go down, I think the next hole might be a 1/4 inch, 1/2 inch, and 1 inch. Okay? So as you go down the hole, as you go to the left, the holes get deeper. But what are you seeing here? All this block is sitting at the same temperature. It's been sitting on a hot plate for hours. Okay? So it's all come to thermal equilibrium. It's at one temperature. Now that Kirchhoff had said that all the holes should look the same, but they're not looking the same, right? The little graphite hole on the right is already white, but the 3 from the perfect reflectors are not. Why? Because they're manifesting what radiation is in the room, not in the hot plate, right? It's what's in the room that's penetrating these things, and they're not able, they can't do work, so they can't produce the white radiation that the graphite hole did. Okay? So the graphite is white because it did work, and the other 3 could not do work, and that's why they remain black. And then as you go over to the left, you see that now it's a mixture of radiation coming in from the hot plate that's captured in the hole, and then radiation from the room. So that's why you now see these crescent shapes inside of this. There's 2 types of radiation in here. One corresponding to the temperature of the room, and the other one corresponding to the temperature of the hot plate. So again, this proves that Kirchhoff cannot be right. And the reason is that the perfect reflectors are unable to do work. They'll sustain whatever radiation is given to them. It has nothing to do with thermal equilibrium. So only graphite was able to do work, and perfectly reflecting cavities will display incident radiation. So if I can only convey this message to the world, this would be it. That because of Kirchhoff's law, Planck's equation remains unlinked to the physical world. And this is a central thing here. That Planck wrote an equation. So we had this light, and Planck gave us the equation for it, okay? But he never told us what caused the photons. What was the physical setting? What were the energy levels? What were the transition species? But in every other spectroscopic method, and I'm a spectroscopist by training, we can always identify these first 3. But because of Kirchhoff, and it's independent of the nature of the walls, Planck's equation was never linked to the physical world. Now, the reason that's important to you is it enables solar physicists to say that we can produce a black body spectrum from anything, or it enables the Big Bangers to tell us that they can get a black body radiation from the creation of the universe. They can't. Once you link these things, once you explain why do you get a thermal photon from graphite, whatever mechanism you use, everyone will be bound by it. So all of this theory will collapse. So this is actually a terrible blow to astronomy here.
The picture that we have of the CMB today is that it was the CMB was produced as a result of decoupling. You know, when radiation decoupled from matter because the various charges combined to form neutral hydrogen and so forth. And the picture is that all of this happened about 380,000 years after the Big Bang, very, very early on, right? Much earlier than star formation and eventual galaxy formation and so forth. But the honest truth is that this is all theory. We don't actually have any hardcore evidence that that's really where the CMB happened, where it was produced, and that was the mechanism that produced it. We don't see recombination lines, for example. And it's true that the sensitivity of the instruments is not yet great enough for us to have conclusively detected the lines, but until we actually see recombination lines, this idea that the CMB was produced by recombination is just a theory. There's no experimental verification that it happened. And perhaps even more tellingly, if the picture of the CMB having been produced early on as a result of recombination is correct, then there shouldn't be any frequency dependence in the fluctuation spectrum. In other words, the spectrum was produced in a medium where the most important physical process, Thomson scattering, is independent of wavelength of the light. But yet, when we look at the data from Planck, say, we do see evidence that the spectrum of fluctuation changes with wavelength. So that again argues against the recombination picture. We don't have a compelling argument yet, but what I'm getting at is that this notion that the CMB was produced 380,000 years after the Big Bang due to recombination does not have yet any experimental confirmation. On the other hand, it's possible that the CMB may have been formed in part due to dust processes. And if you look back and ask when would the dust have been injected into the intergalactic medium, it would have been at the time when population 3 stars started forming, which actually corresponds to a redshift of about 15, not the redshift of 1081, which is what we currently think is where the CMB was formed.
This is the Penzias and Wilson antenna, the horn antenna at Crawford Hill Laboratory that the measurement was done on. And we won't read this whole thing, but basically it says we got a 3.5 Kelvin signal and we couldn't explain it. And nowhere in the Penzias and Wilson papers do we talk about diffraction of signal into the horn. So nowhere in the Penzias and Wilson papers of 1965 can one find any discussion of the diffraction of nearby signals into their horn. Now people wonder, well, how did an NMR guy get into this mess, right? And here's the answer. So Ed Purcell is the discoverer of the 21 centimeter hydrogen line in the galaxy. He discovered it 1 year before he won the Nobel Prize in 1952 for NMR. So we're both dealing with radio techniques. They're doing spectroscopy, so am I. It's basically our samples are different. And this is a picture of Ed Purcell's horn that he used to detect the 21 centimeter line. So these fields are actually much closer than people would imagine. So to tell an MRI person that he cannot look at astronomy is just a little too far reaching, considering that Ed Purcell was one of the first radio astronomers. Here's a radio telescope from the University of Illinois. Well, that's kind of exposed to everything, right? That could be coming in from the side. Here's the scoop antenna at Green Bank, which was used to monitor atmospheric changes. Well, that's pretty much the Penzias and Wilson antenna, pretty much the same kind of design. There's nothing sophisticated here. So the COBE satellite is completely unshielded from microwave radiation from below, which can easily diffract into the COBE horn, the Pheris horn. Significant diffraction problems are very likely to exist for every other instrument on Earth except one. So now we come to Harouni's antenna. And people have attacked that, hey, this is just an old antenna here. Who cares about a result from an old broken down antenna? Well, when the result from Dr. Harouni was done, it was not a broken down antenna. It was new and he was testing it. And then he found that there was no signal from space. So how could that be? So this is showing inside the antenna on the right here. You see the detector. So this is actually 5 meters across because this is not a parabolic antenna. It's a hemisphere. So it doesn't focus onto a point. So the signal comes into kind of a bell-shaped detector here, which is deep within the antenna. Okay, so that's very different than the parabolic antennas that you've seen. Okay, so what's important about that is his antenna self noise was only 2.6 Kelvin. So it has to have some self noise. So where's the signal from the Big Bang? You're missing. He should have had 6 Kelvin or so. He called it an edgeless radio telescope. So that's why it's unique. So any signal that's approaching from this side, it's edgeless. It's going to prevent diffracted signal from coming and hitting the detector. So note how the detector is protected from most diffracted signals. And again, if you look at a modern radio telescope, they're above ground. They do nothing to prevent diffraction, and their detector is wide open. It's imprudent to speak in terms of black bodies without noting, as Kirchhoff did, the constraint of the enclosure. So the astronomers, they need an enclosure, and what they try to say is, well, we did have thermal equilibrium at recombination. Well, this is just an invention of mathematics. They don't know that. Kirchhoff's law is his requirement was very severe. You have to have an opaque enclosure. So thermal equilibrium with an opaque enclosure, not just thermal equilibrium. The enclosure must be opaque. Well, that never existed in the Big Bang. So you cannot set a temperature. A source which is not at 3 Kelvin can produce such a signal if it sustains, in addition to emission, another means of contending with internal heat, namely conduction and convection. Alternatively, a source which is not at 3 Kelvin can produce such a signal if it has structure wherein one bond is much weaker than another. And of course, I've argued that this signal is coming from the Earth. So I especially like this quote by George Smoot. So he's testing a radiometer at Berkeley, and this is what he writes. An invisible patch of water vapor drifted overhead. The scanner showed a rise in temperature. Good. This meant the instrument was working because water vapor was a source of stray radiation.
We don't quite understand how much of the dust, how much of the light from stars is being absorbed by dust and where exactly that happens. And so we have different measurements of how much submillimeter light there is, so far infrared light there is from the dust, and how much light we think is missing, and then how much light actually is missing. And that's where the problem, like we're trying to tally up the light to make sure that we know how much is missing and how much is being re-emitted as the far infrared, and those two numbers don't seem to quite add up yet. There seems to be about a factor 2 off, and a factor 2 in astronomy is still something to worry about. We like to be exact, and especially these things tend to add up over distance. So it's important to figure out which one of these kinds of dust is dominant.
The most well-studied dust ring around a star ever. And then somebody widened the field of view and realized there was 1,000 AU dust belt around it. They have been looking at these things with the kind of wavelengths to see dust for a decade, and they missed 1,000 AU dust belt out around it. We are not good at seeing this stuff at all. This one was published in the Astrophysical Journal. It is official what many people have thought and hypothesized. There is a widespread presence of nanometer-sized dust grains in the interstellar medium of galaxies.
The structure, especially in the interstellar matter, seems to be very self-similar. So if we look at the largest scales, it looks pretty smooth. But as soon as we look in any kind of detail, it breaks up into filaments, and those filaments break into filaments, and those filaments break into filaments.
Sophia. They did spend a lot of money on Sophia. It was supposed to help solidify this force of gravity model for the formation of stars and star clusters. They found out that not only are magnetic fields and turbulence, and when you see turbulence in this realm, they're talking about plasma turbulence, plasma interacting with itself and interacting with electric and magnetic fields, not what many of you might have experienced on the flight here into the rain and clouds yesterday. But so magnetic fields and plasma turbulence are not only involved, they may dominate the creation process of these stars and star clusters. The missing mass of the universe is tracing the cosmic filaments. Now, this is where mainstream scientists say, okay, but that was just the normal matter we knew was missing. We still have all this other stuff we need to look for. The problem is, finding all of the missing matter scattered about is very different than finding it in a current. And we know that these cosmic filaments feed material down onto galaxies. So when you have all this material and it's not spread out, it's actually in the cosmic filaments. It's traveling the same direction, feeding galaxies. It is a current. There are magnetic fields wrapped around it. They see protons, they see electrons in these things. And so matter is no longer just matter when it's in a current. Okay, if it's spread out everywhere, it has its gravitational attraction. If it's in a filament, it has its gravitational attraction, but it's got a lot more than that, doesn't it? It's creating magnetic fields, it's creating electric fields. And that way, a baryon, a proton, is no longer just a proton. It's now doing a lot more, and it's affecting a lot more. Okay, well, if we have these, if this really is a whole magnetic mess, then we should be really seeing these with every little structure. And so what you see here, when you see a blue circle, that means the magnetic fields are wrapping towards you. Red means they are wrapping away from you. And you should see the white filaments in the middle of them. Every single one they've looked at, there must be a current hidden that they cannot see running through the filament because the magnetic fields are uniform and wrapping around it, just like you'd have a magnetic field wrapping around electricity going through a wire. Now, they can't see the electricity going through these filaments, but it must be there. Otherwise, the magnetic fields would not be uniformly wrapping around it like this. So, probably the most incredible filament of all isn't a filament, it's a sheet. So the Musca filament was one of the brightest filaments in our galaxy that we can see, but it turns out we're just looking at it edge on, and it is actually a flat sheet. In the bottom right picture, I have a bunch of colored lines drawn. They are all magnetic field directions, but what you'll notice is the green ones are all of the filaments that are coming off of a main cloud. The main cloud would be in the top left part with the large blue line running at a slight angle. And then down towards the bottom of the extended filaments, you can see that those filaments have their own filaments coming off, again, at 90-degree angles. Not only are all of the filaments that they're seeing have the magnetic fields either wrapped around them or embedded in the length of the filament, but when they're coming off of a larger cloud, they're all perpendicular to one another. This is the right-hand rule of electromagnetism. That's why they're forming where they're forming. And so this is that little blue pink thing up at the top there. That's what they believe the Musca filament, Musca sheet actually would look like over on the left. If you could take it and turn it so you could actually look at it sideways, it's a flat sheet. And the icing on the cake, those little white things, those are other magnetic fields. So they not only notice the magnetic field cutting through the sheet of Musca, but there's perpendicular magnetic fields all throughout it as well. This is a 100% electric structure. There's no way for gravity to do these things. When Sophia comes out and says that stars and star clusters are about magnetic fields and plasma turbulence, the predecessor of a star cluster are these molecular clouds. These are the someday to be nurseries of stars, or so we think. And so there's no way for gravity to set this up where not only do the magnetic fields trace all the filaments, but they're all perpendicular to one another. It's mainstream in the sense that that's the right-hand rule of electromagnetism. It's not mainstream in the sense that that's not supposed to happen out in space. That's not what's supposed to be dominating out in space. It's supposed to just be gravity, random collapse, chaos, things like that, and it's just not the case.
In 2018, a NASA article, basically out of nowhere, mentions our existence in the plasma universe, which was a baffling sight to see for those of us who know how many plasma universe physicists don't think dark matter exists. One of the projects that has received very little attention and which we really don't hear much about, is poised to be the next leap forward in our understanding of the real dynamics of cosmological constituents.
I'm Anthony Peratt from Los Alamos National Laboratory, U.S. Department of Energy. I started out in plasma cosmology under the Nobel laureate Hannes Alfvén. Alfvén had written a book in Swedish called Cosmic Plasma. Well, I know something about Swedish, and certainly I know something about English. So I wrote the first English edition of Cosmic Plasma under Hannes Alfvén's name. One of my fortes was supercomputer computing of large-scale matter. So for 12 years we did teraflop computing, the full set of Maxwell's equations on matter, electrons, ions, and neutrals, only three-dimensional. In other words, real-world calculations. And from that we were able to, much to our surprise, calculate the full evolution of plasma and neutrals acting under gravitation, plasma acting under electromagnetic forces, and recover the evolution of plasma collected in the universe as it evolved towards a galaxy and eventually a spiral galaxy.
Alfvén, Peratt, Birkeland, the three founding fathers of the plasma universe. If there is an accretion of the intergalactic medium in those regions, meaning outside of the galaxies, then the orbital velocities of neutral hydrogen clouds are determined not only by the gravitation of mass inside their orbits, meaning that if you have a bunch of stuff where we think there's empty space outside of the galaxy, if it's there, I know we can't see it, and most astronomers don't think it's there, but if it just happens to be there and we can't see it, the math says you don't need dark matter anymore. And I'm going to go back up here. This is what Christian Birkeland said. We have assumed that each stellar system in evolutions throws off electric corpuscles into space. It does not seem unreasonable, therefore, to think that the greater part of the material masses in the universe is found not in the solar systems or nebula, but out in the empty space. What we didn't know is that the active plasma nucleus, supermassive black hole, whatever you want to call these things at the centers of galaxies, they are feasting on many more stars than we realized. And in addition to feasting on many more stars than we realized, they are blowing out an enormous fraction of that which they take in, up to 80%. So this whole stuff is getting eaten by the black hole? No. A lot of it's getting shot out, the cosmic jets, and a lot of it is getting blasted out. Well, here's the thing. We know for a fact from the observations that the stars are going in. We know for a fact that the material is getting blasted back out. But they look in the inner galaxy and that plasma's not there. They look in the spiral arms and that plasma's not there. It's been blasting out from the center of the galaxy for billions of years, but they don't see it in the middle. Where must it be? It must be around the galaxy. There's nowhere else it could be. Now, that's some pretty impressive circumstantial evidence, but it's still just circumstantial at this point. So let's see if we can gather up some more real evidence for that material being out there. Well, you remember this? The most well-studied dust ring around a star ever. And then somebody widened the field of view and realized there was 1,000 AU dust belt around it. There is a widespread presence of nanometer-sized dust grains in the interstellar medium of galaxies. We're going to come back to that in just a minute. Because this is when the whole thing should have fallen apart. Does anybody know what you're looking at here? Do you remember this is just a couple of weeks ago, the lost light of Hubble. The white areas on here, that's areas where they still have no return. Just looks like black empty space as far as you can see. The colored areas are the galaxies that they know. The black areas around them are the dust and gases and other things that they knew of. The gray stuff around those is the lost light of Hubble. So around all of these galaxies, where they could not see before, is a whole bunch of dusty plasma, a whole bunch of emitting sources exactly where they were predicted to be by the plasma universe, and in the place where, mathematically, dark matter dies. But getting into this dusty plasma and why this is so problematic for cosmology, because it is a trickster. It really is. And so I'm just going to read some of the stuff up here. When they were doing these experiments with dust on the International Space Station, there was not chaos, but they noticed order imparted on the dust. It lined up, it formed waves, it formed crystalline structures. Now, they determined that these crystalline structures and the lines and the waves were based on electric fields. That's how they were lining up. It wasn't based on gravity. And so when you have these regions around the Earth, around the solar system, around the galaxy, interacting with electric fields, forming these crystal patterns of dusty plasma, it basically means we are looking at the cosmos through a kaleidoscope.
The national labs have been gaining traction in these plasma universe discussions. In the weeks just following Sophia's magnetic and plasma discoveries in star-forming regions, SLAC showed it was the magnetic fields powering cosmic jets, not a function of the accretion disk energy. And then Lawrence Livermore at Berkeley saw electric currents driving those field actions. Their torus jet modeling mirrors what we see across the country at Princeton's Plasma Physics Lab and their NASA collaborations. There's that recent Navy patent as well for a super technology using plasma magnetohydrodynamics, and expressly states in the patent the device works because we live in a plasma universe. So we have now arrived at this weirdest possible point in physics, haven't we? Grant money and university professors mostly chasing dark matter, along with the popular media articles, while some NASA teams in the National Plasma Labs are all seeming to be chasing something else.
They can't seem to get the correct results, and they seem to think it's due to some magic essence that they have left out, and they call it dark matter. So as a result, you have several hundred professors, graduate students that are working towards their PhDs, so on, that are pursuing dark matter without any knowledge of what it is. There's no missing matter at all. We just had a lot of experimental data that we could compare the simulations to at energy densities that universities, graduate students, professors, associate professors, full professors, professors emeritus simply did not have access to. We did. Now, the universities really, and I had a choice once I had a PhD. I could go into a university and get tenure eventually, or I could go into a national laboratory and work with real data, real equipment. My gosh, the equipment that we burned up in the first millisecond of a nuclear explosion underground was just more than all of the universities in the world could afford. They simply can't afford to lose that kind of that investment in high power, sophisticated measuring equipment so quickly. And plus you're working in an environment where you're working with real world physics, not the physics that you learn in textbooks, that maybe 5 years old, 10 years old, 200 years old. This is real world stuff.
Next, we wonder about the 3D simulations that they do have now, and one of the most renowned is Illustris. The problem is that the mistakes that drove matter physics into darkness have progressed far more quickly than the reduction in price of supercomputing. And what this means, practically, is that since the universities attained the ability to work with this level of computing, they have included dark matter and dark energy to a degree dwarfing the luminous matter, and have lacked the luminous matter being discovered by the weak, the dust, the plasma, connecting galaxy clusters and clusters to the cosmic web, surrounding the galaxies and controlling star-forming regions. The natural extension of these discoveries is the electrical action at various scales throughout the universe.
Let's say I burn toast in my house, and I mean really burn it. I put it all the way up, I smell it burning, I see the smoke, and then I just kind of turn my back and I let it go for a few more minutes. Then let's say I eat the piece of toast anyway because that's how I like toast. And then I take the toaster and I throw it out the window. Then I bring you into the room and I say, find the source of that smell. You have no chance because I've eaten the toast, I've thrown the toaster out the window. All the evidence is pretty much gone. All the evidence you'd want to really understand it. And that's what we're talking about with a potentially extinct current here. Something caused these filaments, and it wasn't gravity, to form like this, like lightning throughout space. And that thing really might not be there anymore. We might just be seeing the aftermath. The smoke trail from the meteorite that blew up 4 or 5 seconds earlier, and there's no more light from it. It's just the essence of it. It's the smell of the burnt toast that's left over. And so now we come back to a story that I think most of you probably know about. They flew Cassini through the water jets, the South Pole of Enceladus. Magnetometer, hot and running. Langmuir probe, hot and running. They detected phenomenal magnetic fields and only 5% of the requisite electric current. So that is a satellite flying through the electric current. We call that in situ measurement. And it detected 5% of the electric current. This is important for 2 reasons. One, if we can fly right through it and only detect 5% of the current, we see nothing from Earth. Looking out into the cosmos thinking, oh, well, we don't see these electric currents in the cosmos. No kidding. Good luck seeing them if you spotted 5% in situ. But the explanation for why it was hidden, the charged particles of the current were actually being attracted to and hidden by dusty plasma. The dust was actually hiding the ions. The reason they were not able to see the current of charged material in the cosmic web was because of the dust. The exact same thing they ran into in Enceladus. And not a single astrophysicist or cosmologist has put these two together. The same problem that they ran into at Enceladus, which should have given them a clue about how pitifully they see electric currents in deep space, they have already run into with the cosmic web. Oh, well, that's where the normal matter is flowing in that current. We just didn't see it because of the dust that was surrounding it. It's right there. It's right there on a plate. We have a number of new models of the galaxy that have come out just this year. And I've spoken to some of these folks. Some of these folks definitely know the plasma cosmology individuals. These are some of the models that are based on what came out of either one of the national labs. This is what they say we're looking at. And obviously on the right there, we're looking straight down through the axis of the cosmic jet. But they say this is what's actually in the center of the galaxies there. The number one model that's coming out is this torus jet model. Regardless of whether or not it's a black hole, a plasma nucleus, what's around it is a torus and a jet. We don't know what's down there at the exact center. People have a lot of good guesses. But what's just outside of it is observationally undeniable. It's a torus and a jet. And this is what you get when you have that energetic point. And so in the image on the far left where you can really see the jet going up and down and the torus around it, you can't see the full Z-pinch there of everything coming into the middle with the torus wrapped around the waist of the Z-pinch, so to speak. But that's what we've got there. And they fade as they go up because they're losing energy. It's more dark mode rather than glow mode plasma as you get way, way out there, and specifically as it starts to arch back around and make the larger torus. But you can see the interior of the torus here, and this is Billy's first try over there on the right, just doing the fundamentals and turning on the power. He created the jet torus model right there before our eyes.
After the 2019 Observing the Frontier conference, the months that followed brought with them a flood of discoveries, illuminating the pathway forward. Sophia continued her charge, demonstrating that magnetic fields are responsible for action at larger scales, all while Alma confirmed Sophia's previous discovery about the importance of those magnetic fields in smaller star-forming regions. We began to see genuine attempts at scaling up these principles to cosmological scale, and we're seeing those published in major physics journals. Plasma universe, magnetic universe, electrodynamic universe. Coulomb is just another way to say it. At the galactic level, we're seeing tremendous advances in magnetic modeling of a large-scale coherent structure and pattern. This is opposed to the random, chaotic, nova-driven field paradigm that operated for years. The regions between the galaxies and the cosmic web were the final remaining piece of the puzzle. The missing matter is still being discovered at an incredible rate, still just hiding in plain sight. Just outside the galaxies, they discovered that all the material outside the visible stars is co-rotating with the galaxies, indicating that the galactic rotation problem may disappear entirely with more observation. And how that material gets to the galaxies is even more amazing. They come in filaments, currents, moving in a helical vortex, spiraling down onto the galaxies directly from the larger filaments of the cosmic web. That is electromagnetic action, not random chaotic gravity. And so to summarize where we've already discovered the dominance of electromagnetism and luminous matter, it's the star-forming regions and the star-forming rates, the molecular cloud structures, the dusty filaments, active galactic nuclei and their electric current and magnetic field torus jet model, with the luminous matter surrounding the galaxies, with how it rotates, with how it gets to the galaxies in the first place, and with that largest scale structure, the cosmic web. Well, and right, this is the appropriate question at this point. This is actually about the time when the more seasoned professors began to remember Alfvén Klein cosmology, the predecessor to the plasma cosmology that Dr. Peratt is talking about and we're all talking about. And even though it is a bit different, a man named Jim Peebles in 1993 basically thwarted the charge of what they called the plasma dissidence to supersymmetry, dark matter, basically looking at non-luminous matter, things like that. And the two problems were that with Alfvén's initial models, there were some disagreements with the cosmic microwave background. We've heard a couple of things about that already here, haven't we? But also, and more importantly, there were these missing high-energy photons from annihilation events in the cosmos. And well, we've seen they're not really missing anymore. It seems that we keep having to report these super high-energy photons that are breaking records for the detections. And so it really is a different situation now than back in 1993, especially since we're learning that there are some tensions, Hubble, Planck, expansion, cosmic microwave background. We really do need to get these new instruments up there and see exactly what they're able to tell us about the universe at a large scale. And you know, speaking of the larger scale on this, you know, Dr. Peratt's open letter to the scientific community now has dozens of signatories from the field, dozens more in related science and research fields. It's not shocking that the national labs do seem to be nailing it. There are a number of people on that signatories list that are from the national labs. It's not shocking that Peratt did it in Los Alamos. It is, as you said earlier, it is just a shame that his work had to be classified due to the nuclear connections.
I might add that this is a very exciting time to be in physics and to be in the field of astronomy, and by astronomy I mean astrophysical plasmas, because so much data is pouring in now that is providing justification, which we already knew because we'd done the large-scale experiments. It's the physics, the high-energy density physics that you're allowed to get into going into the national laboratories. And this is void in the universities. Name a university and they simply do not have the funds, they do not have the equipment, they can't do high energy density work as is required when you're looking at the universe. The universe is the biggest pulse power generator we have and the largest high energy density media that we can experiment with. So all they're left with is ignorance. And for that reason, a large majority have gone to dark matter, invisible matter, missing matter, ghost matter, so on, to explain the failures of their codes. They publish a good many papers, and really university physics is about publishing papers, be it right or be it wrong. And in most cases, especially with missing matter, it's wrong.
Unfortunately, the situation is even less rosy than the picture painted by Dr. Peratt. I conducted the interviews for this Infomentary, a dozen others that didn't make this Infomentary, and there were numerous other interactions via phone, Skype, email, even in person, with no less than 95 of the professors currently teaching these topics to today's youth in the United States, Canada, Australia, and Europe. There was a disturbing trend that I seemed to notice as I was talking to professor after professor, and many of them were not shy at all about admitting this. They are grossly incapable of keeping up with all of the science that is coming out that might potentially affect their field, might potentially affect their work. Now, there are 3 reasons why this is the case. First, professors are busy. In addition to any research or paper publishing or experiments they might be doing, they probably have to teach classes. They have to grade papers, they have to grade tests, and there's also an enormous amount of administrative work that goes into the individual students, the department, and the university as a whole. Second, this is actually not one field, but many fields rolled into one. Astronomy, astrophysics, astrophysics of galaxies and galactic dynamics, magnetic fields, plasma turbulence, large-scale cosmology, dark matter, black holes, nebula, gaseous and dusty star-forming regions and their interplay all together, each one a very specific and highly specialized field of science. What it takes to be a player, publishing in just one of them, pretty much boggles the mind. It's very difficult to keep up with many high-level fields of science. And that brings us to number 3, which is the one that most of them identified themselves as being the major problem. There are so many places where this information is coming out, and there are just only so many hours in the day. The Astronomical Journal, the Astrophysical Journal, Astronomy and Astrophysics, the Astrophysical Journal Letters, monthly notices of the Royal Astronomical Society, Nature, Nature Astronomy, Physics of the Dark Universe, Physical Review D, and Cornell's preprint archive, 5 days a week. We're talking about 50, 100, sometimes 200 new papers a day. And they're not all going to be relevant, but you have to scan through all of them. And a good dozen to 3 dozen probably are relevant. It's just not possible to keep up with all of those other things when you have a professorship, when you're doing your own research, leading your own research, when you have all those other responsibilities. It really does require a full-time, dedicated passion for keeping up with all of these material. And the interesting thing is most of them have the passion, they just don't have the time.
Miss Alfvén periodically, yearly, would go back to Stockholm, Sweden, and I guess he would go back in the summers and not in the winters. I guess he was not enthralled about the cold of Stockholm in the winter. Also, it gets very dark there very early, and at that latitude, there's maybe about 5 hours of sunlight, and the rest is all dark. They call it the blue hour, going into these different phases. And so I spent actually two sabbaticals at the Royal Institute of Technology in Stockholm with Alfvén and his colleagues. And there I picked up more direct information. After all, it was Alfvén that got me started in this field. And that is also in the 2015 edition of my book. I also spent time in Norway at the institute, the Norwegian Institute for Physics, and there spent a great deal of time with another professor touring Norway, going up to the Northern Lights section of Norway, Svalbard Island, where I could see Svalbard Island. That day I was quite a runner, and I used to run along the shores of Norway up north, where I could see Svalbard Island, which is all covered with ice, and it's got polar bears. So I had no interest whatsoever of going there. However, it did prepare me for another task that I was given, and that was in the final days of the Soviet Union, before they became the federated state. We were doing nuclear experiments at the Nevada test site, and also nuclear experiments at Novaya Zemlya, which was the Soviets, the Russians' nuclear test site in the Arctic. And I was team leader for experiments there, where I collected a great deal of information. They also have a lot of ice. They also have polar bears. And luckily, I'm a shooter. So they gave me an AK-47 just in case. I remember one of the Soviet scientists saying, "If you come face to face with a polar bear, you are no more." And that's true. So you've got to be quick. You've got to have a weapon.